Okay, so in this video we're going to talk about z-scores, which tell you how many standard deviations above or below the mean an observation is. Now that's generally useful for giving a rough sense of how rare an observation is. We'll say more about that in a couple of minutes. We're also going to take a look at how the empirical rule can help us decide on percentiles and sort of rough percentages of scores that are below or above a certain score. So that was kind of left hanging. We didn't do a lot with it from the previous section, but it really becomes useful today. So let me kind of remind you what the empirical rule says. First off, you have to have roughly a bell-shaped distribution. So we think of it as kind of being symmetric and unimodal. Usually is an indication that you've got a bell-shaped distribution. This curve you can think of as just like an idealized histogram, so that we're used to, or at least we've had some experience in dealing with histograms, which look a little blockier. But just to kind of give an overall sense of what the shape is, we use this idealized version, and we call that a bell curve. Now, the empirical rule tells us when you have such a distribution, roughly what percent of your data you expect to be within 1 standard deviation of the mean, within 2 standard deviations of the mean, and within 3. Now, specifically, the rule says that if you have that the amount of data that you should have that's within 1 standard deviation of the mean, so that would be 1 standard deviation below would be -1, and 1 standard deviation above would be +1. Between those two values, we should have about 68% of our total data. So most of the data, right, is in this sort of middle region, pretty close to the mean, which is the dotted line here. Okay. Within 2 standard deviations of the mean, so we go out 1, 2, or to the left, 1, 2, down to -2. Between these two values, within 2 standard deviations of the mean, we should expect 95% of our data to fall in that range. So vast majority of the data between -2 and 2 standard deviations. And then you get just about everything if you go out between -3 and 3. So if you're within 1, 2, 3 standard deviations of the mean in either direction, then you should expect 99.7% of all of your data to be in that range. So it would be really unusual to get something that's not in that range, and that's actually one of the reasons why we have a criterion for outliers that is 3 standard deviations above or below the mean. So if you had something that was 3.5 standard deviations above the mean, that would be a candidate for being an outlier. And if you had something that was, say, -4 standard deviations below the mean, or 4 standard deviations below the mean, so a -4 on the graph, that would also be an outlier. Now, one of the things I want to point out is that these numbers that I've been referring to, these are, in fact, z-scores, right? Because we're just counting standard deviations above and below the mean. So 1 standard deviation above the mean is a z-score of 1. 1 standard deviation below the mean is a z-score of -1. And so another way to phrase this first percentage is that 68% of your data should have z-scores between -1 and 1. Right? So again, when we speak of a z-score, we're just talking about how many standard deviations above or below the mean we are. And we use that as a measure of rarity of an observation. And in fact, if we have an observation with a z-score bigger than 3 or a z-score less than -3, those are outliers by our z-score or standard deviation criterion for outliers. All right, now how do we apply this to a real situation? The example given in the notes is about ACT scores, where the mean ACT score is given as 23 and the standard deviation is given as 3. So I think it would be useful to mark values along this that correspond to z-scores of 1, 2, 3, -1, -2, and -3. So I'm going to do that now. The center is always the mean, so that's going to be an ACT score of 23. Now, one standard deviation below the mean would be 23 minus 3, so that would be a 20. One standard deviation above the mean would be a 26. 2 above the mean would be a 29. 2 below the mean would be a 17. 3 below the mean would be a 14. And then finally, 3 above the mean would be a 32. Let's see, it's not going to show up very well. Let's do it over here. 32. So these would correspond to z-scores of 1, -1, 2, -2, 3, -3. And we'll verify that in just a moment with our calculations, actually. We'll start now. So what's the z-score for a score of 26? Well, using our formula, we take the score itself, subtract the mean, which is 23, and then divide by the s, the standard deviation, which is 3. So here my z-score is going to be 26 minus 23 over 3. It's 3 over 3, and that's a 1. So a score of 26 has a z-score of 1, and note that's where we put it to begin with. What about for 17? 17 minus 23 over 3 is -6 over 3. That's a z-score of -2. 2 standard deviations below the mean, and that puts us right here where we noted it before. Let's see. This is a typo on chalkboard. So, I want the z-score for an ACT score of 29. So that's going to be 29 minus 23 divided by 3. 6 over 3, and that's 2. Right, so there's my 29 ACT score. All right, we could do others as well, but that's just enough, I think, to give us a sense of how the calculation is going to work. All right, now we have some questions about percentiles, or percentages or areas. The first one is asks us what percent of all of the ACT scores should be between 20 and 26. Well, these are exactly one standard deviation above and below the mean, and so our empirical rule says we should have 68% of the scores there, right? So that's this middle version, that middle area that's outlined in pink. So this should be 68%. All right, well, that one was straightforward. The next couple, you have to do a little bit of geometry and some addition and subtraction. So we want to know now the percent that's above a score of 26, right? So that's this area, and we're asked to figure out what percent that area is. Well, this takes a little bit of work because all we are given are middle areas. We know that the middle area here is 68%, which means we're missing 32%. But the distribution's symmetric, so that 32% is evenly split between everything to the left of 20 and everything to the right of 26. So it's 16% each, which means the percent above 26 has to be 16%. So one more time, 68% is the middle area. There's 32% that's not in the middle. That 32% is equally split between left and right, so 16% each. Now what about below 26? Well, we can do this a couple of ways. The easiest way is to use what we just did, right? If 16% of the data is above 26, then 84% is below 26, right? 100% minus 16%. But notice, we could also do it just thinking about areas to the left. Right? So below 26 would include the 68% in the middle of 20 and 26, plus an additional 16% that's to the left of 20. So that would be 68 plus 16 is 84% also. So either way gets us to the right place. All right, what about the percent below 29? All right, well, that 29 is one of our special points, 2 standard deviations above the mean. The 95% of our data lies between 17 and 29, right? So that means 5% of the data is not in that middle. But that 5% is equally split on the two sides. So we should get 2.5% is the area to the right of 29, and 2.5% is the area to the left of 17. So the area below 29 is going to be 100% minus the 2.5% that's above it. So that's 97.5%. Or we could approach it with left areas. To the left of 29 until we hit 17, that area would be 95% of the total, and then we have an additional 2.5% left of 17 for a total of 97.5%. So I just want to point out that to connect this to the language of percentiles from the notes. So the fact that 84% of scores are below 26 would mean that 26 would be called the 84th percentile. And if we, I guess we could kind of round either way, but we would say that, do a percent there. The percent below 29 is 97.5%, so we would call 29 like the 97th percentile or the 98th percentile. Now, what about the 99th percentile? Here, we're after a score that has 99% of all the data less than it. And it looks like, right, because we've got 99.7% between 14 and 32, that we could say that roughly 99% of the data is going to be less than 32, right? There's a tiny bit out here we could add, 0.15%. But in total, this is as close as we could get from what we know, right? 32 is the 99th percentile. And then finally, we're asked whether the points 12 and 35, that's a terrible 3, are outliers. And to determine that, with what we are currently looking at, we have to just check to see if there are more than 3 standard deviations away from the mean. So we've already marked that 14 is 3 standard deviations below the mean. 12 is less than 14, so yes, 12 is an outlier. We could confirm that with a z-score. 12 minus 23 divided by 3 is minus 11 thirds, so that's about minus 3.67. Right, so z-score less than 3, outlier. Similarly, 32 is the cutoff for 3 standard deviations above the mean, so that 35 is an outlier also. It's bigger than 32. And in fact, the z-score of 35 would be 35 minus 23 is 12 divided by 3. It would have a z-score of 4. Okay, so both of those, 12 and 25, are outliers. So you've got some similar calculations to try in the worksheet. So please get started on that, and I will see you on Monday.